Why, thank you. So, good afternoon, everybody. So my name is Antti. I come from F-Secure, and I'll spend the next roughly 45 minutes to try to explain what modern malware looks like and how do we actually analyze or reverse engineer it. So I realize that there's probably varying levels of knowledge of this field, and it's not the typical talk that you'll see today. So I'll start by explaining a bit what reverse engineering actually is and why do we need it. So this is not really a concept that's only for software. We do it for software, more specifically malware, but this is a thing that applies to anything. It can apply to airplanes or tanks, and it's the process of trying to figure out how things work. In the context of software, somebody said it's the software development cycle backwards. So you try to go from machine code back to disassembly, decompilation, to source code, back to the design of the application if possible. We do it for malware because many times we need to understand how malware works, if only not to add a detection for it into an antivirus product or to explain to a customer what their problem actually is and what they should be worried about. So that's what it basically is. And today we'll be talking about malware. So I thought I'd split this maybe 50-50. So 50% slides, 50% actually reverse engineering malware, and I'll spend the first half explaining what kind of malware do we see and what are the people that we see behind the malware. So I'll start by online criminals. To put it simply, these are the people that write malware to make money. And it's not actually just a malware, it's sort of like an ecosystem. Sorry about the buzzword there, but I'll try to explain what I mean. So, your mom or the average user is going to get infected nowadays in many different ways, one of them being just to browse normal websites. This is the Los Angeles Times website, which for roughly 7 weeks was serving malware. Sites like this usually do it accidentally. Nobody hacks into them, they just serve ads. And of course you can buy ad space from these sites, and the bad guys know this as well, and they buy space for malicious ads. So you see the little ads there on the page. Oftentimes those lead to malicious sites, and that's called malvertising. So it's basically a way to get people that don't visit dubious websites like porn sites onto a malicious site. Now, then waiting on that malicious site, if you're unlucky, is something like this. So this is not what the victim sees, this is what the attacker sees. So this is the control panel for Black Hole. Black Hole is one of the most popular exploit kits. So you can basically rent it. This works in a rent model where you pay a few thousand euros and somebody gives you a server that hosts Black Hole. And Black Hole basically is a compilation of different exploits. Java exploits, PDF exploits, Flash exploits that are served to the browser that is redirected to a site hosting Black Hole. And the idea, of course, being is that somebody wants to install software or malware onto your machine, and he wants to do it automatically. So you need a bunch of exploits. Nowadays, Java, you might have many opinions about it, but that's usually the source of the vulnerability. So many people run old versions of Java on their machines, and that's where these exploit kits usually reap the benefit. So that's the method of installation. And what do they want to install? Well, this is probably familiar to many of you, but I'll pick an example that I'll show later on the actual functionality and how do we analyze things like this. But one piece of malware that somebody might want to install is a Banking Trojan. So this is the login page for Rabobank in the Netherlands. And their logging process works like so that you basically type in your account number, your password, and then this one-time login code that you get by putting your bank card into this device and basically typing in your PIN code. So this is what the website looks when you don't have an infected machine. This is what it looks like when you have an infected machine. So actually it shouldn't look any different. They just messed up the styles for the in-logging button there. So what's basically happening is that the malware lives in the browser. it modifies and sees all the network traffic going in and out of the browser. So it's able to detect that, okay, you went to your bank login page, it's going to intercept the data that you're going to send, and then basically send it to the attacker. So in this case, when you log in, you see something like this. In Dutch, it means please wait a second, and there's a timer running down. So your information was sent to somebody, most likely in Eastern Europe, that's now logging into your bank account. And the two-factor authentication doesn't really help there at all, because the attacker can now send further requests back to this screen. So next you'd see a request to authorize the transaction, which the user normally believes because it's coming from the bank. At least it's on the bank web page. So this is one way to make money. And there are others, of course, but what I really wanted to maybe make a point about the online criminals or the financially motivated attackers, that it's a working ecosystem where you don't really have to have technical skills to implement this. You can buy the exploit kit. The Banking Trojans that you saw, that was Citadel. You don't actually code Citadel, you go to the Citadel store where you buy an instance of the Trojan. This is the CRM system for the Citadel Banking Trojan, where people are able to vote for the features that would be next included into the malware. So somebody's saying that it would be a really nice idea while we are hooking the browser to also be able to search interesting files like passwords.txt and banking.doc. And well, 80% of the users agreed, so they're going to include that into the next build. So that's why it's so popular, because it doesn't require any technical skill. So moving on to maybe something more interesting is the attackers with the other type of motivation. So now we're talking about online espionage. I'm not going to say nation-state attacks, I'm just going to say online espionage because the actors are sometimes more tied to the governments and sometimes less. But the intention is different. Now we are not looking to steal $100 from somebody's bank account, but to mostly gain valuable information. So the malware looks a bit different. You'll see that in a bit, but also let's say the marketplace looks a bit different as well. So there is a marketplace in this area as well. Here is a French company, so everybody always expects that we go to the Chinese and the US NSA. But here's an interesting French company called Wupen, and they pretty obviously state on their website what's the business of this company. So they sell government-grade exploits to lawful intercept missions. They sell these to national security agencies. So in the way that you would buy black hole from a Russian underground market, if you are an online criminal, if you are a nation state, this is where you go for your exploits. Of course, you can develop them themselves, but this market is something that's expanding all the time nowadays. So here's one way to get your exploits if you're a nation state. How you spread them looks a bit different. So now we are not owning Los Angeles Times. You might be owning other sites, but mostly how we see these exploits being spread is through what we call spear phishing. So basically, emails sent to people in companies in places where they have valuable information. So you get an email with an attachment that looks something like this. All of these are actual exploit attachments that we collect from our backend systems. It's quite easy to spot these things. We have, well, a lot of the things that we do are automated. So once we get to the demos, you'll see manual ways of doing things, and my lab is very small, so what we do is we try to automate everything we can. And this is one of the things that we've automated, where we take documents that we get in through various feeds, we put them to virtual machines that have old versions of browsers, PDF readers, Flash players, and then we see what happens. So all of these were collected from those systems because we noticed that at the same time the document was opened, an executable was dropped onto disk at the same time. So that doesn't really happen when you normally open Excel files. So this is the way those exploits are spread. We won't talk that much about reverse engineering exploits. It's not that different, but requires a bit of a different skill set, and I only have 45 minutes. So we'll only look at the malware. And in the government case, there's also a similar ecosystem. This is an interesting company I picked. There are many like this, not just in the US, but I picked a US company. called Endgame. I don't know if you can see, this is the About Us from the Endgame Corporation web pages, and they describe what they do. And if you actually read through that, at least I didn't get any idea of what this company actually does. I mean, they are problem solvers, risk takers, and inventors, but they don't really say out loud what they do until you go and see their job ads. So here's one for a cyber intel analyst, where they mention that you'll be using Endgame toolsets to assist and train government analysts in computer network operations. CNO. CNO is if you haven't heard of it, it's basically a military term. Wikipedia has it nicely explained. So CNO consists of CNA, which is computer network attack, basically disrupting computer systems, or CNE, which is basically intelligence gathering using these toolsets. So from the job ads, it's quite obvious what companies like these do. And in the media, it ends up looking like something like this. Probably many of you saw this 2 weeks ago from Belgium. So Belgacom came out with the information that their mobile routing system was compromised. So the routers that route traffic from mobile phones got owned. And interestingly, Belgacom, being in Belgium, is the mobile operator that handles most of the traffic from, let's say, the big EU institutions, the European Parliament. So this was pretty obvious who this was. It was the UK, this time with GCHQ, penetrating these systems with the help of, let's say, most likely their allies and companies like Endgame. So this is maybe the two categories, and what I thought I'd do next is try to go through what does the malware actually look like. So what do these banking trojans look like? How do we analyze them? What does malware that does things like this look like, and is that somehow different? So I'll close the PowerPoint for a while and let's go to actual demos. So let's start with the criminals, so the financially motivated folks. I have the banking trojan that I used in the previous demo here. It's called Citadel. It's a single executable. So mostly we deal with Windows malware nowadays. There's stuff for Android, but not nearly so much. And most of the files that we look at are going to be Windows executables, and so is this one. So it's a Windows executable, roughly 270K in size. And I'll try to use mostly tools that are available to anybody. We have, of course, a lot of internal tools, but those are maybe not so interesting for you guys since I can't give you the access. So most of the tools are either free, or then at least they're available in the public market. So let's look at sample.exe. First tool for me to usually look at samples like this, just to get a quick overview, is a hex editor. I use HT, there are many other good ones as well. And from this we can already see that indeed, yes, it's a Windows executable. Anybody that's ever looked at one in a more detail knows the magic marker in the beginning there. MZ is the start of a Windows executable. HT can give me a better view of what the headers look like. So the PE headers, if I want to know, well, is it actually a DLL? Is it an executable? What are the imports, exports, things like that? A hex editor is a good first tool for that. You can also look at the code with this one, but it's not the most convenient way to start actually analyzing any code, which is something you shouldn't be doing in the first place anyhow. You should start with other things. The most laborious way of looking at this is to actually start reading the code. So let's do another quick check. I'll just run strings against this. With any string longer than 6. So this is another cheap trick. Always use cheap tricks. No need to do anything further if you can already find what you're looking for with things like this. Strings gives me the list of imports, so the functions that this executable is importing from different libraries. But it also gives me the first hint that I might have a bit of trouble in my hands here. So there's a URL and some information related to installation problems. So what this thing is using is actually an open source installer called Nullsoft. Malware does this for many reasons, one of them being that it makes the analysis more difficult. So all the actual executable content is compressed. There's no use for me actually looking into the code that you briefly saw there, because all I'm going to see is the Nullsoft installer code. So let's move on with the cheap tricks. Rather than actually trying to look at what it does, let's just run it and see what happens. For this, I use a separate virtual machine, just to be able to revert back and forth if I make mistakes in the analysis. So I have the same sample here. It's not called sample anymore, it's called Bieber. There's a good reason for that. If you name your samples sample.exe and then run them, oftentimes they refuse to actually do anything because they're going to check their names against common names that are used in automated analysis environments. So better name it something else. You don't have to call it Bieber, but not sample.exe. You'll notice the icon doesn't really make sense either. It's a Java icon, and it's the Excrobat reader. But okay, moving on. So what I'm going to do is I'm just going to run it, but before that, some simple instrumentation into place. So many of you might have used Process Monitor before just to look at system problems or analyze a bug. That's a really nice way to see an overview of what's going to happen when this malware runs. So I've done a bit of filtering. Typically, this will show everything that's happening on the system, all the write operations, all the read operations. I'm just going to filter out everything that isn't a write. So I'm only going to be interested in new files being created or new registry keys being created. So that's the first filter there. Let's apply that. Hopefully there's not too much noise here in the background. And then let's run Bieber. So a bunch of stuff happening here. Let's not go through all of this, but I'll show you some interesting tidbits. So we see a bunch of temp files created. They all start with NS for Nullsoft, so that confirms that, yeah, probably it's the Nullsoft installer. Bieber also writes a bunch of other DLLs. So DLL is a shared library on Windows. And now it's actually trying to connect to the network. So let's let it do that. The next interesting thing we see here is that Bieber actually stops doing anything, and another temporary process is started. So it's a multi-stage installation, which ends up like so that all of these temporary processes actually disappear. And the only thing we have running in the end, if we scroll down a bit, is going to be Explorer.exe. So what the malware does is basically inject most of its code into Explorer.exe, which is the process running the shell here, the thing I see, the user environment. So the only thing that we see repeating here are repeated registry writes to a run key. So what Citadel is now doing is repeatedly installing a launch point into registry, so to make sure that it always runs after a reboot. And it does this to avoid being removed very easily, so you see these writes happening all the time. So that gives us some idea. We didn't have to look at any code. We already know roughly what it might do. We know where the run key is, so I can actually remove it right now without looking at any code. I'll show you another quick thing here with a debugger. So first look at another tool, WinDebug. So what I'll do is I'll start the browser. In this case, I'll start Internet Explorer. And I'll take a debugger, and I'll attach it to IE. I'll tell you in a moment why. So WinDebug for me is a nice tool to look at what's happening on the system. Not so much actually debugging, but seeing what's going on in memory. And I mentioned briefly that, these banking Trojans, they live in the browser and they modify the traffic. So I'll show you what that means in practice. So WinDebug, the interface is full of various little command line options. One of them is LM. LM will just list all the modules that are loaded into the browser. Modules meaning usually DLLs. So the DLL that implements the networking traffic functionalities is the WinSock DLL. WS. Let's see what it was. I forget. WS232 is the one that IE uses for network traffic. So there's a nice little trick here that you can actually use to detect pretty much any banking Trojan. WinDebug has this command called check image. What that does is basically takes the DLL from disk, it takes the DLL as it loaded in memory, and it looks for differences. So let's see what it finds. So it says I'm scanning the image in memory, and it reports that it has found these differences. So there's a 6-byte difference, for example, in the send command. So these bytes have been changed to these 6 different bytes. So what it's basically doing is hooking the send API. So let's see what's there. U for unassemble or disassemble, and send. So this is what's in memory right now. Anybody know what a push followed by a ret actually does? Do we have any x86 assembly fans here? Well, that's just a cumbersome way of doing a call. So you're calling a sub-function, but instead of saying call address, you're pushing the address of the function onto the stack, and a ret actually returns to the address that's on top of the stack. So it's trying to confuse me. Many times there's a jump there that's much more easy to read, but a push ret is trying to confuse somebody that's analyzing the system. So let's take a look at that address. That's actually going to be code from the Citadel malware as it's loaded into the browser. So there's another tool that actually all the banking Trojans, no matter what they do on the outside, they actually have to intercept these functions, and they do them pretty much in the same places. So this is a really easy way to look for a banking Trojan. But let's say I want to understand a bit more. Let's say I want to understand what else does the malware do besides drop all these files. Then the usual way for me to do this is to try to start analyzing the code. And to do that, I have to go through the nullsoft compression layer on top, and maybe something else as well. But let's try to do that. So we'll leave Citadel there. I'll just revert the snapshot. I'll come back to this in a bit. And let's start poking at the files. So we have sample.exe here. We know that it's basically using nullsoft as an installation method. Nullsoft is open source, and it's a nice little application in the way that I don't really have to understand how it works, and I can get files that have been compressed by using tools like 7-zip. So if I list the contents of that exe, it's basically a zip file with the code that unzips it included. It will show me, well, these are the files that the person that used nullsoft actually compressed inside it. Randomly named DLLs, 3 of them, and then one file that's a different extension, this nube.peru file. That's the biggest of all of them. So it looks like that might be an interesting file. So I've extracted all of these. You can also do that with 7-zip. And basically, yeah, we have 4 files. So now there's a temptation to again go and look at the code and see what's happening. I've done that as well, and what's actually happening is one of the DLLs is in charge of basically running the whole thing. One of the DLL generates a key, and the other one does the decompression. So you can look at those DLLs and you can figure it out by yourself. I made this mistake. Instead, what I should have done is just to take a look at the file that I'm interested in, which is the first big file. So hex editor. Looks a bit scary, but believe it or not, I actually tried this with a few of the analysts in the team, and I said, can you tell me what's the encryption here? Just by looking at this data without looking at any code. And it's actually quite doable. This is not magical crypto. It's basically, well, I'll tell you this, it's an XOR crypto. Can anybody tell me the key? Well, this relies on the thing that if I expect that there's going to be some null bytes there, some padding there, the XOR with any byte against the null byte is going to be the byte itself. And you see these repeating patterns here. So likely that's actually the key. I don't have to look at any code. Let's take a try. One of the reasons why I like the hex editors is because I can do things like this on the fly. So HT has this thing called block operations, which allows me to do simple XOR operations against the data. So I'll just do it for the first 100 bytes in hex. It looks like it's a 4-byte key, so 4 bytes is a D word because it's JEBA. So for each of the D words, I'm going to read it. Read 32 little endian, O for the offset of the byte. And I'm going to XOR it with a key that we're going to guess is this repeating pattern here. Of course, we have to reverse the bytes because this is little endian. If you remember the endiannesses, we have to switch. So you see here we have 6A, 65, 62, 61. So we just reverse those. Tell me if I make a mistake, but 61, 62, 65, 6A. Yeah, so you see the magical MZ there, and what we have is the next layer of encryption. So let's see. I did this earlier for all the bytes, and I saved the file to disk. So what we actually expect with most malware like this is several layers. So don't be too happy yet. Probably you're going to have the next puzzle ahead of you. So let's look at that file decompressed. I have it here in another folder. And at this point, we can move on to the mode of actually looking at the code. Next layer, I can already reveal, is not going to be as easy so that I can just guess what's going on. So the last tool, or the second to last tool, what I'm using today is called IDA Pro. There's a free version. It's basically a disassembler, meaning that it can turn machine code into the actual instructions. And it has a plugin to actually do decompilation that works sometimes, works rather well, but the problem of turning this into C, which was the original language, isn't always so easy. So, second layer. Again, you see that on the left you see the functions that IDA managed to extract from the binary, and there's not too many. This is usually already a sign that this isn't Citadel itself, it's another layer of compression. On the top you see a bit of color coding, so that little tiny blue bit there is the code, and this big brown thing is a resource. So it's actually just data that you can embed into an executable. So logical assumption is that there's a bit of code there that does some decompression, and the next layer is stored in that resource file there. We could do a similar trick. We can figure out what the algorithm is. We can either replicate it in Python or try to use a hex editor to go through it. In this case, there's a tiny little bit of a problem, and that is basically shown already in the first lines of the code. So indeed, if I show you something, there is another XOR loop here. So these loops where data is being manipulated with an XOR are very common. That's the encryption that the bad guys use. But there's a little bit of a trick. On top of that, there's also a call to a Windows API. So this is largely undocumented Windows API, but it's a function that the malware doesn't implement itself, it's Windows. So Windows has a function called RTL decompress buffer that uses a compression algorithm that's not actually that well documented. So in this case, it's a bit tricky for me. I could write custom code that uses that function to decompress the resources. But instead, I can let the malware do it by itself. So let's get back quickly to the red machine. So I have here now, here's the original file. In the temp folder is the decrypted one. And this made me laugh a bit, so I spent a bit of time actually unpacking this sample this week. So after a few of those layers, you find the second to last layer, and in the description of the executable, there's the string, "I'm sorry for the inconveniences," so I guess they are trying to be polite. So what I'll do is, instead of manually with a hex editor try to get through this layer, I'll just let the debugger do it. And I'll use a tool called OliDebug. This is the last tool. I'll give you a list of these tools if you want to get familiar with them. So this is basically a debugger, but probably not the kind that you're typically used. So this, I guess it can actually, if you have the source code for the application, it could basically load it here. but it's not really designed for that. Most of the debugging that we do absolutely without source code, of course, and OLIDebug is the best tool in cases like that. So let's load beaver2.exe. And well, I did a bit of analysis, and I figured out that, okay, it's going to use the Windows API, and then it's going to do a bit of XORing, and then at this point in the code, everything should be already decompressed in memory. So let's give it a go. I'll set a breakpoint there, and I'll just press play. And quickly, everything happened so that the malware did the job for me, and in the EDI register, which is being pushed there, is a pointer to the executable. So I can look up EDI, follow in dump, and here we see a memory dump where, again, the familiar MZ there in the beginning. And this time, it's the final layer of the executable, so you see different sorts of headers that it's using there, and they are all decrypted. So now we can actually start analyzing everything. But the problem with commercial malware is this was 3 layers. 7 layers isn't uncommon. More difficult layers are more the standard. So that's the most difficult part. Let's take a quick look. I'll show you the examples of things that we might look for that we cannot discover using tools like Procman and just seeing what's happening on the system. So I'll load. This is the final unpacked Citadel, so the one that I got from the memory using the debugger. And we'll look at an interesting function here. I named it already, so all of these names are, of course, things that the tool cannot tell me. All the names are basically lost here, so names of functions, names of variables are not visible, so I had to do a bit of analysis. So this function called check language is called right when this malware is being installed. And if it returns false, then the installation fails. And what it does is basically calls a Windows API called getKeyboardLayoutList, which gets the list of keyboard layouts that are installed, so the keyboards that the user of this machine is using. And then it does a bit of looping to compare those keyboard layouts, which are just numbers, into a global list, G-language list, which consists of 2 values, 419 and 422 in hex. And those stand for the Russian keyboard and the Ukrainian keyboard layouts. So what the author wanted to do is to make sure that this piece of malware never actually installs on a machine where the user is either from Russia or Ukraine. And there are good reasons to do this, because if you write malware in Russia or Ukraine, but you never infect victims in those countries, the law enforcement is going to be much less interested in tracking you down. But these kinds of things you can only find by looking at the source code. I'm going to spend a bit of time looking at the other type of malware, the let's say espionage-related malware. So before that, I'll show you one thing. So on the left, you see the list of functions, and you can see at the bottom there that there's 780 functions. So this is something that you can actually go through. It might take you a week, but you can go through these functions and understand what it does. So let's move away from Citadel and onto the nation-state stuff. So I have a few minutes, so I'll show you 2 things. I'll show you a malware that we think is Chinese origin, most likely from the group called Comment Crew, or APT1. There's a lot of research papers on those. So I'll show you why they're called the Comment Crew. And I'll show you what the malware actually looks like as well. So going back to IDA, and there's a reason why I'm actually jumping straight to IDA without going through all these other layers. I'll show you that in a bit. The malware that the Comment Crew uses, or one of the families, is called WebC2. And I'll open WebC2 for you. So 2 things to note here. 1, there's only 21 functions in this malware. And this is not a compression layer. This is the actual malware itself. This is the whole malware. So when you talk about things like advanced persistent threats, it doesn't mean that the malware is any more complex than the actual financially motivated malware like the Banking Trojans. This is very simple. You'll notice there's no compression or encryption on top of it either. There's a good reason for that as well. These guys know that antivirus companies like F-Secure have heuristics where they say, if a file is packed, or if a file is packed and encrypted 7 times, maybe it's not a good file. Maybe we need to already heuristically block it no matter what it does. So 99% of the time, the espionage-related samples are not encrypted or obfuscated at all. So these guys are called comment crew for a good reason, and actually you can see the reason if I just dump the strings from that file. So it's so simple that you don't really actually have to look at the code a lot to understand what's going on. So here's the command and control server URL that it used. Again, no obfuscation, whatever. And there's a few revealing strings here. Interesting, in the bottom you can also see the folder where the developer were actually developing this malware, which the Russian criminals usually leave out, but in this case they didn't. So what it does is related to these comments here, like table. So it's called comment crew because on the command and control server, the URL that you see below, there's an HTML page, and the HTML page has comments that look like this. And what the malware does, it goes to that HTML page, parses for those comments, and looks for the second stage URL. So they want to be able to flexibly update the next place where the next piece of malware is being fetched, so that if they take down the domain, so that domain is not up anymore, there's no way for me to know what was the second stage URL anymore. And it's called the comment crew because the second stage URLs are always inside these marker comments. So most malware that we see in the espionage side looks like this. It's actually rather simple, nothing fancy. They are bigger, of course, sometimes, but they are not as fancy as the high-level cases. So I think I have a few minutes. So the last one I'll show you is the Flame malware. I have both Flame and Stuxnet on this machine, but let's keep to one of them. It's always interesting to take this laptop into the US with all the malware on it, but don't tell anybody. So Flame is a single DLL, just so that I remember correctly the size. It's 6 megabytes in size. So it is going to take a while to open this file, but let's give it a while. And this gives you maybe the actual problem when it comes to dealing with the certain high-profile cases. It's not that there's several layers of encryption or things like this, which we're actually rather good at solving. It's just that these things are written by big agencies, big subcontractors, and they're actually proper software. So this thing, if I go to the top and start scrolling through the code, you can see that it's quite big. And this is the actual challenge with high-level cases like Flame, so that it's not that it's complex code, it's just that there's so much of it. This one has 31,000 functions compared to the ones that you saw in Citadel. But to kind of wrap this up, skills-wise, it's not much different. These kinds of malware are at the certain level pretty much the same. In this case, it makes sense to know your attacker and their motivation. If the attacker is an online criminal from Ukraine, he doesn't really care who he's going to infect. So he's going to write malware that's obfuscated and packed, and it doesn't really matter if an antivirus product detects it. While if you're writing Flame, then you're going to spend an awful lot of effort into your code, and you're going to spend an awful lot of testing, and the malware is going to look different as well. And it's good to be able to spot. Nowadays, just by looking at the sample already, you know where it was being used. But I hope you got a bit of an insight into what reverse engineering malware is, and maybe somebody got the idea to try some of these tools out. If that happened, then I was a success. But thank you everybody for the time.